Good evening, everyone. Welcome to today's presentation on race against lambda. Let's actually start with a simple definition of what is race condition. And race against lambda obviously looks like a fancy term, but it's actually like managing the AWS Lambda's concurrencies and how we can actually prevent our system from handling same request twice. So okay. Uh, so what are actually race conditions? This is a quote state out from Wikipedia, and race condition or race error is a condition of electronic or software or another system where the system's substantial behavior is dependent on the sequence and timing of other uncontrollable events. So what we are actually trying to say that into the world of software development, risk condition can actually lead to unpredictable and often undesirable outcomes. Today, I'll actually try to take you through one of our incident which happened to one of our microservices uh, due to the concurrency issues of AWS Lambda and how the risk condition occurred and what are the preventive steps we have taken to solve that issue. So to summarize what the race conditions in Lambda and how to visualize it, as I think this image will work. And as you can see, this is a reference image of Usain Bolt running forward. But to sum it up, that here there will be multiple Lambda container, same Lambda container, obviously trying to process the same request, and the first Lambda will obviously win. Then the rest of them will be discarded, and this is what we actually call the rest condition. Actually, if all the lambdas are actually running in parallel and trying to complete the request parallelly, then there might be some unpredictable or uncontrollable events happening in our system. So what are the agendas of our talk today? Obviously we'll actually talk about the rest conditions, but there are more agendas here. Like first one is actually we'll talk about our old service architecture, what was the architecture of our old service was which caught this race condition, or the incident happened. When race conditions are created in lambda, so obviously a discussion in there. So obviously one of our race condition incident, then different strategies we could have applied and their pros and cons, and as there is a business requirement as well. So there are different strategies to solve this problem, but what are the problems or what are the pros and cons of different strategies for our business case? This is something we'll be actually discussing on the new architecture we implemented to handle the risk condition for our businesses. Then things we need to keep in mind while implementation. Lastly, safeguards you need to keep in mind if you try to implement this kind of architecture on your system to handle this kind of scenario. But the real agenda is, I think you guys all know, is me trying to win this month's gem competition. So as you can see, so I think that there is a mismatch here, but I think I can get in the top position after this presentation. So let's start with a story time. Let's talk about what actually happened and when actually our this incident happened. So once upon a time, one day, one of our sister product. So by sister product, I mean, as we are actually a part of a cross-functional team, there are multiple products and we call them sister products, and we ourselves a product and we provide service for our sister product, some services. So we have a service where we have some our service which is integrated with our sister product is that they'll be able to publish to XCMS instance via our service, and they have an instance there as well. And one day they decided to release a new feature for that XCMS instance solution, and the rest is actually history, like bucket ATH. And what happened next is that this is what happened, and our system went haywire, boom, and our system wasn't actually working as it should have. There are some unexpected scenarios happening, we'll see in the future slides what actually happened. And but our system wasn't actually working as it should have, and customer was actually disappointed, as because this is not what the customer was signed up for. So let's first take an overview of actually how a sister product work for the CMS solution. And so first, whenever they create an instance, they send a post request for draft article creation. So that request is handled by us. We create a draft article. uh, okay, not no issues there. Later, whenever an asset is added to their instance, the user press the done button, and um, the sister product again sends us a post request with that asset upload, and we actually take care of the asset upload as well. So there is no problem there with the old architecture and old system. It was actually going smooth, and there was no issue there, because there was some kind of like thing needed to be done before a post request was sent. But what happened is that our sister product released a new feature, and which is the instance will now send us the post request whenever an asset is added to the instance. There is no need for pressing the done button anymore from the user end. But we this is our maybe a vague observation from us, but I think maybe the user kept on pressing the done button anyway. But what we saw is that for one single asset upload, we are actually having multiple requests at the same time. And this is what actually like happened. And the service which was responsible for uploading asset to the XCMS system is now uploading multiple assets of like one asset multiple times in that system, which was duplicate content from the customer's end. And this was a problem. Obviously the customer didn't sign up for duplicate asset upload, right? They wanted one asset uploaded one time. They don't want one asset uploaded multiple times. That's how waste of resource from their end as well. And what actually what was the reason for it? Because uh, we are actually trying to debug what was the reason for it, and which we are actually saying why our system is not working. And finally we found an answer why. So this is an high level overview of our previous system architecture. On the left hand side you can see that this is actually a high level overview. There are some internals things here and there, but to understand the system in a high level way, for SP we are denoting sister product as SP. So SP will actually like send a post request to API gateway to one of our lambda. That lambda will actually ensure like validate and everything, later then upload the asset to the XCM solution, and provide a feedback through the sister products message sender service. So this is how the old architecture and old system worked, and it was working fine. What happened with the new feature is that now our SP was sending multiple requests, which was actually triggering multiple lambdas, because lambda can spin up on demand, and we didn't have any reserved concurrency or provision concurrency for that system. So if there was 1,000 requests at that point of time, 1,000 lambda will spin up, and it will all of them will start processing the request. So what happened that for one single asset upload, there was multiple requests coming from our sister product, and multiple identical requests, if I may say, and all of them was actually trying to get processed by different lambda containers. So this is a incident retrospective. So what we actually had to invest some time trying to because this is something which is actually rarely happening, but when it happened it was actually like catastrophic. And we had to like identify the root cause of it, and we saw that this is one example obviously, but there are some multiple scenarios where multiple lambda container. Here you can see in the screenshot, there the only two lambda container was running, but there are scenarios where three or more container was running at the same time. So what happened is that whenever a request came, initial request came, like within a short deviation of time, like initial upload asset request obviously, then within a short deviation, like 3-second deviation of time, another request came. It was something which wasn't intended, and what was happening is that two lambda container was spawn up at that moment of time, and two of them started doing the same thing, and uploaded the asset twice in the XCM system. So uh, you guys might have a question like why did why we should have a like safeguard preventive measures or something in our system before even we delivered this service to the customer, right? Or else our system was flawed from the beginning. Yeah, we did have a safeguard, and that was we have a traditional DB lock set up for that asset. But the database we are using is DynamoDB provided by AWS, and which is actually eventually consistent. We didn't have any we didn't like there are some settings in the DynamoDB where we can actually increase the provision read or something. I don't remember the exact term, but you can set up the thing in that way to get the latest update one to one. But what our DynamoDB was actually even still consistent, and even we write something in our table, and there will be some latency before we can retrieve that information to our system. So there was that thing, and as you can see, there are another reason why our DB log failed is that as you can see in the this flowchart diagram, uh, first we have a request which comes from our SP sister product. Later we start processing and validating that request. Then in the next phase we check for that asset log in our database. But before locking that asset to do the rest of the task, we actually have to check. Like we have another product on the sister product, which is the MAM sister product, and we have to check there if that asset is available there or not, because there are some scenarios where we got the request from our sister product, but that asset was not available in our MAM sister product. So we have to like return the customer saying that okay, that asset is still in process or in progress in the MAM sister product. We'll start working on later. So this was the then after everything is done, we ensure that okay, the map sister product have that asset, and then we log that in the DB and start the upload. Also, there are some scenarios where sister product did send the asset, but there was no useful information in the payload. For that reason, that we have to discard those requests as well. But we'll talk about it later. So what is the easy solution, right? You guys might have identified this by now, that what we can do is that we just swap the workflow a little bit. Like why not lock the asset first before checking the mem asset? But that is something which is a risky move from us, because for instance, as we have seen that multiple requests are coming within a short span of time. What if like then what we have to do is that when the request comes, we'll process and validate, then check for DB log, then lock it in the DB, then start checking the MAM sister products. If that is not available, then we have to unlock that asset, right? Then start the upload. There are failure cases in each step. I didn't actually write it in the flowchart, but I think you guys got the gist of it. But what if when you lock that asset in the DB and check in the MAM sister product for that asset availability, another request came with the valid asset, but due to the lock, that request is discarded. This is something which might come or which might happen. For that particular reason, we can't actually lock our asset first before checking that asset is available in our map system product. Because if that scenario comes, then that's a denial of service, right? Then the user will see that there's no asset is uploading on the system. It's actually like better to have multiple asset upload than no asset uploading in the system, right? So this could have been one solution for us, but obviously this wasn't the solution for our businesses. So let's see what are the other steps we could have taken. As mentioned right now, because our DB was still eventually consistent, so there are some things, if another request came and we just discarded that request before the DB lock was released, then there might have been some unintended thing might have happened if we have taken this approach. So this is what have been written in the slide, and let's go on to the next slide. So now I want to show you the one of the most tempting solution for AWS Lambda. So there is a thing called okay, let's just see the image. So we can actually mix the lambdas reserve concurrency to one. In that way, that lambda container will actually run one time. At least one container of that lambda will run. There won't be any multiple lambda container running in parallel. So this is actually a tempting solution for us, but obviously there is also a drawback for it, because although what are the problems, what are the problem, what might be the problem with this template? Because this might look a suitable solution, but there is another problem which might happen if we have done that. That is the bottleneck problem, which is a common scenario in our line of work. So if we actually like think of it in this manner, that for instance we actually like set the reserve concurrency to 1. So that means that even if like a lot of requests comes, only one container will actually do the work, no one else will actually run up. But what happens when there are multiple instances of work? Like we can see that like our sister product have like multiple instances where multiple customers are working on it and they are sending requests, right? Then what will happen? There will be a bottleneck problem there. Even there might be some denial of service as well, because the API gateway to Lambda, the requests are being held for a certain minute period of time. If that's more than that certain period of time, the request will be like discarded. So there is a risk of denial of service there as well. So uh, there, those are the some of the solutions we would have taken. But let's see what we have done with our system later. So this is a version 1 integration of a system. I think I'll talk about the next version later, but this was the initial setup, the initial architecture we have like designed. And there was something we need to took into consideration before designing this architecture, because we have a time limit, because our sister product was already in production, the feature was already there and it was working for the customers. But our system wasn't able to deliver the services we promised, and we have to like deliver this fix within a short period of time. I think it was like 5 days or something, and we have to like brainstorm, identify, and develop and integrate this feature with the system within that 5 days or short period of time. So that was a challenging task for us, and we had to took into consideration, because we could have like there are diverse solution for one thing, right? But we do have to take which is the suitable and the easiest and the fastest solution for us. And this was the one thing which was working for us. So what we did is that in our architecture, where the sister product put a request to our API gateway and the Lambda was running, but instead of that Lambda taking care of uploading to CMS, what we did, we connected that Lambda to a SQS system, and later that SQS system, the message queue service of AWS, that SQS actually like trigger another Lambda, which is a consumer Lambda for that SQS, which will be responsible for that XCMS system's asset upload and everything. And this particular SQS is actually a FIFO queue. So every request that comes, it will be actually like serialized, and all of the requests will be like performed in a first come first serve manner. So even if multiple requests comes, all the requests will be like tunneled into that queue, and all the requests that come first will be served first. And like that's how the system worked. And so obviously you guys might have identified like there is a drawback with our fast design, right? I think you guys might have seen like from the audience would like to mention what might be the like drawback of this system. um, okay, so the drawback is actually like as you can see, their SQS actually provide us one kind of like failure mechanism. Like if some service fail, SQS will retry it on our behalf if we don't say anything. And this is something which is actually beneficial, because there are different scenarios where thing might have failed. So obviously a retry mechanism obviously always welcome, right? So SQS is actually like responsible for handling those kind of things, and it will if we don't set any configuration for it, it will actually by default try to retry. But now the new problem we faced is that, as this is a FIFO queue, and we don't have any like custom retry mechanism for our end, or we actually given the every responsibility to SQS. The new problem we face is that if we see these three images from the first like queue, the block queue, you can see the red and green sequence, right? So if it I take the green one as successful task and the red one as failure task, you can see that the green one will be executed perfectly, right? But the red ones will actually turn up in the first message of that queue in the second iteration. like there is a batch size you can determine. So if, for instance, we have given a batch size of 10 for that SQS. So first few requests which are successful will actually execute, and the few of them which have failed will turn up in the queue's first messages. So this is what happened. Like the failure messages were actually in the first of the queue, and it was actually trying to retry it in like multiple times infinitely. So this problem actually event this problem actually this issue actually created a denial of service for our customers for a certain period of time. So this was something which was not intended. So what we did with our system is that immediately we actually try to identify what was the root cause of it, and we actually like saw that, yeah, our system was missing DLQ, which is the date letter queue, and we integrated that data layer queue with our SQS. So what we did now is that we set up a redrive mechanism. So the SQS will retry it obviously, but for a certain number of times, like 2 or 3 times. After that, it will send that or discard that message to the DLQ, and DLQ's lambda will be actually responsible for sending out the customer saying that, okay, this is something which actually failed, and like it will actually take care of the rest. But our main service, our core lambda, which is connected to the SQS, won't be actually like there won't be any denial of service there now for our customers. So you guys obviously have this question by this time on your mind, is that how did we handle the bottleneck problem now? Because uh, as it's a FIFO queue, obviously there should be another bottleneck in our system right now, right? So how did you do it? How did we do it? This is a typical overview of how the AWS SQS FIFO work. So the SQS FIFO queue actually takes all the messages in a first come first serve manner, and depending on the batch size, for instance, we have given a batch size of 10, it will take the first 10 batches, and later it will start working on the second batch or the rest of the batch. So what if we actually followed this way, then there was a problem that if you can see that in the request, like there are A, B, C, or if we say that these are the 3 instances, and 1, 2, 3 are the number of requests. So obviously the B instances got priority in the queue, and there will be a denial of service for the A request, right? There is not a denial of service, but there will be a delay, maybe like few seconds of delay, and the service will be eventually executed. So what we did is that there is a way to say that, okay, batch these groups all together, and that's it's mentioned at group ID. So in SQS, you can actually say that, okay, group this kind of message in this queue. So it will actually create an internal pipe where similar group IDs message will go in one pipe, and different groups of message will go in different pipe. So that's why we actually like resolve that bottleneck problem we had. So now our system will actually try to ID, and obviously the grouping ID is actually based on the customer's unique ID and obviously the instance ID. So there won't be any clash with another instance or another customer. So that's how we actually resolve that bottleneck problem on with the AWS SQS FIFO. And now our system will actually try to take the batch of same request altogether, and another lambda will actually trigger like consumer 1, consumer 2, as in like consumer 1 will be consumer 1 lambda, and consumer 2 will be another lambda container which will be taking care of the second batch. This is how the new architecture worked, and how we actually was able to resolve both the bottleneck problems we might have, and also the race condition we had with multiple duplicate requests with our system. So there are some observations like there, as you can see, there is a lot of discussion during this talk, and there's a lot of observation from us because obviously this kind of new system which we design is that there will be flaws, right? But what we could have done better is that this is some of the observation, because for say this the first one is always create the DLQ first before creating any SQS queue. This is something which I have like missed, because the DLQ was a key feature and key integration which was needed, because our queue was actually like going haywire, and we were actually stuck with, okay, why there was a denial of service. But this was something which was like there was two ways to manage it. Like either create a DLQ first before creating an SQ. There is always a good thing to have a DLQ, or uh, always handle the error yourself. This is another way to handle that issue. But always the second point is actually like always there is always good to have some kind of alarm setup for that SQS, because we have seen that there are multiple messages queuing up in our queue, but we didn't notice that until like one of our customer or said that okay, this is not working as it should have. And good thing that after the deployment we were observing our system, so we were actually was the first to respond to that issue, and was able to like identify and resolve it within like 4 hour 5 hour time frame. Always good to have some kind of alarm setup for the SQS queue. That third point is always I have already mentioned. In the SQS queue, there's a thing I don't like to share is that if we don't handle the error ourselves, SQS actually will retry that whole batch. If for instance there is a 10 batch of messages and one of them failed, and SQS will actually retry that whole 10 batch again, if we don't handle the error ourselves. But we can handle it ourselves and send the failed message back to the SQS. That's something which we can handle. That's a good approach rather than letting SQS handle the error themselves. So always obviously the fourth point is a common one. Always good to have trace IDs and some kind of dual logs in the CloudWatch, because what was a good thing for us is that we, instead of having one trace ID, we have actually four trace ID. And that was something which was actually really helpful for us, because we did was able we did was able to like find some meaningful insights with one of the trace ID, even if another was there wasn't any information with that one. So that was something which was really good for us, and it's actually really good to have some kind of debug loss in the CloudWatch. Okay, so the last threes are kind of like subjective to team. Like before this is something which we all should do, because before starting we always should read the documentation really carefully, and then you are done with the work, again read the documentation for any kind of mistakes. There might be some mistakes, right? And you are deep now, your feature is like March to dev, but you are now deploying to production, right? And again read the documentation for a final check. So this is something subjective from team to team, because if you are working in a large distributed team, obviously there will be another team member or another there will be a multiple team member, and there will be Q&A and everything to ensure that your feature is actually ready for production, right, before it goes to production. But if you are working in a small team, then it's your responsibility to identify and say that okay, these are the things I need to do, and it's your responsibility to make sure that your feature is actually production ready before it goes to production, and there is no problem with it. Last thing is actually like the first thing we should have done is that if you're stuck with a problem, share and ask for help. There's multiple people in your organization who might have done similar task, and I'd like to like acknowledge Rasul Bhai and Rahan Bhai for the tremendous help for with this problem. I actually bothered them a lot, but they actually provided some useful insights on how we can actually like implement the system. So yeah, stuck with the problem, share and ask for help. That's always a good thing to do, even if you are not don't know anything about these kind of systems and everything. Yeah, so I'm almost done with the presentation, and if you guys have any question for me, feel free to say it now.